All right. I haven't done anything yet, but thanks. Thanks for that. So, welcome to this talk on API security pitfalls. So I'm going to talk about common mistakes I often observe in APIs, things you should be aware of, things you may have done wrong in your own applications, and we're going to take it from here. I have a lot of content, so I'm going to dive right in. Then after that, once the application is loaded, it's going to access an API, it's going to fetch some data, it's going to perform some operations, and essentially what I'm going to talk about is what can go wrong, or what you should be taking into account when you have such an API being accessed by applications. What I'm going to talk about here is going to focus on web applications. So I mainly focus on web application security, but the same will hold for other types of APIs, and many of the principles are fairly universal, so will be important for every one of you. By the way, there's still people coming in, so you can move a bit towards the front if that's possible, so we can fit as many people in as possible. One of the reasons I want to talk about API security is because it's getting a lot more attention. And this is a screenshot from the OWASP Top 10, the first proposal for the 2017 edition. And the OWASP Top 10 is like a list of the most common security vulnerabilities. And one of the issues they wanted to add there this year was underprotected APIs. It didn't make it into the second release candidate and the final edition, but the sentiment is still there. And the sentiment is that we're building these new types of applications, these new types of systems with APIs, and we're seeing all kinds of vulnerabilities appearing there, and all kinds of the same mistakes being made over and over again. And I believe one of the reasons this didn't make it is because, in fact, a lot of these issues are not new. A lot of these issues occur in a similar way in traditional applications. A lot of these issues occur in a standard GSP application without an API. Only now, in an API world, they're a lot less obvious to observe and probably a lot more dangerous as well. Before we start, a small word about me. My name is Philippe De Ryck. I know it's a very difficult name for non-Dutch speaking people, so no offense taken there with the pronunciation. Essentially what I do is I'm a trainer. I help people build secure applications. So I go to companies, I give multiple day trainings on how to build secure applications, how to assess threats, and how to implement defenses. I built an online course for a university on web security, which is available for 2 more days, which is short notice, I know. There's probably going to be new editions next year, and the content will remain online as well. So there are videos on a lot of security topics, so if you're interested in that, definitely check it out. And then finally, I'm also organizing or co-organizing the SecOpDev course in Belgium, which is a week-long course in security. So if you ever want to visit Belgium, that's the perfect reason to come there in February next year. But enough about me, let's talk about API security. One of the most fundamental things that you should be taking care of is HTTPS. It's really, really, really important. I'm not going to go into detail on HTTPS and how to configure that and stuff like that. I kind of assume that you know that HTTPS is important, so we're going to take this as the baseline. And if you don't have this, well, everything else we're going to talk about is going to build on top of that. So I would probably make deploying HTTPS one of your top priorities. Just a few words about HTTPS. First of all, there's no excuse to not use it anymore. So people used to have excuses like, yeah, HTTP is still better in performance, or we don't need it, it's only public information. That's all gone out the window. HTTPS today is mandatory. There's free certificates from Let's Encrypt, so there's plenty of support on enabling that. You can automate your whole HTTPS deployment, so please do that as a first step. One of the things with APIs is if you have HTTPS, in general, you used to have a redirect. You used to make the first request with HTTP, then the server would tell you, no, I'm going to use HTTPS, please go there to load the application. With an API, that disappears because you're accessing your API directly. You're making a call from JavaScript or whatever directly to your endpoint. So you don't need the HTTP redirect, but only if you don't serve other resources on that same domain, of course. That's one of the things. The HTTP redirect is still one vulnerability, and if you remove that, you actually are able to make your API more secure. And the second step you should do then is enable strict transport security. And strict transport security is a response header. I know it's difficult for you to see on the bottom of the screen. There's screens on the side as well, and the slides are online on my Twitter feed, so you can look them up if you want to follow on your phone or whatever. Essentially, the header is strict transport security, and it tells the browser, for the next number of seconds, you should always use HTTPS when sending a request to me. Even if the user types HTTP, even if the application wants to use HTTP, doesn't matter, upgrade to HTTPS by default. And essentially, that helps you get rid of any redirect, any kind of attack on the network that tries to downgrade to HTTP, stuff like that. So it's fairly simple to enable once you already have HTTPS and using HTTPS for everything. That brings us to the first security pitfall. I have about 11 or 12, I'm not sure, so we're gonna have a lot of content to cover here. First one, don't use HTTP anymore. Get rid of it. If you only have an API running there, switch to HTTPS by default, enable strict transport security, and you're good to go with that one. As I said, this was the baseline, so let's try to dive into a bit more detail on your application side. The first thing I want to talk about, this is an example from Facebook. Somebody found a vulnerability in Facebook and actually got a lot of money for it. I think they got like $15,000 in bug bounty for finding this one vulnerability. And essentially what happened is Facebook has this recovery mechanism where you can reset your password, and they send you a code by SMS, for example. You enter that code and then you can reset your password. And he figured out, the code was 6 digits, and he figured out that on their beta platform, there was no rate limiting on calling that or submitting a code to reset your password. So you simply go to trigger that mechanism for your account and then brute force all potential 6-digit numbers until he found the code, and he would be able to reset your password. And essentially that's kind of dangerous vulnerability that got him a lot of money. That brings me to the solution to this. You should be rate limiting your API. Unlimited access can have severe consequences. People can really easily automate certain calls. It's really hard to detect these automated calls, and essentially, before you know it, they have extracted a bunch of information, or they have brute forced certain features of your API. There's several strategies you can use. There's no one-size-fits-all solution. You can do it per connection property, for example, per IP address. But that is often a problem if you have net-style networks where everybody is behind the same IP, like the conference here. That would be problematic if you want to rate limit based on that. But you can also do it per user account, per endpoint. There's essentially plenty of strategies available there, plenty of libraries offering a feature like that. And actually, one of the funny things is many APIs have a rate limiting feature, but for business purposes. So many APIs have like a free version and a paid version and an upgrade plan and whatever, and these are essentially rate limiting mechanisms. So you have like 15,000 calls per month, stuff like that. Of course, the window for rate limiting there is much larger than something you would do for security. So security is about seconds, maybe minutes, not about a full month. But the mechanism behind it is essentially very similar and very the same. If you want to do this in practice in an API, there's a very handy HTTP status code that you can use, and that's 429, too many requests. So essentially, what you can do there is you can send that back to the client. So you can add an additional header, the retry after header, informing the client, by the way, you should wait X seconds before you try again. And of course, you're using an API, so you have a client-side application. You can gracefully handle these responses and tell the user, like, okay, sorry, you tried too many times. We're probably going to have to wait a couple of seconds before we try again. And if it's an attacker, then of course, this will keep him out. It's also going to inform him how long he has to wait, but that doesn't really matter if you implement your rate limiting properly. That brings us to the second one. So we're getting started here. Not rate limiting API, calls to your API is definitely something that a lot of APIs miss. It seems like unnecessary, but before you know it, you can get hit by such a brute force attack with serious consequences. One of these examples of serious consequences is actually extracting information. This is another example from T-Mobile. You may have heard about this a couple of months ago. Somebody figured out that they could access all account details from T-Mobile customers. And the reason he could do that is because they used the phone number to refer to an account. So if I knew your phone number and I knew you're a T-Mobile customer, I could go there, enter your phone number as the identifier, and would get your account details. It doesn't sound like something you want. And actually, this happens a lot in practice. And here's a code example of how this happens or why this happens. This is a code example from a tutorial online. The references are in the back of the slides if you want to look at it later. And essentially what you see here is the typical way of setting up a REST API and accessing stuff. This is from a to-do notes example. And you have you want to get a task and you look it up by identifier, and essentially when you find it, you return it. This is how every REST API starts, how your first Hello World example starts. And that's where you start to build on. Of course, in a real application, you need authentication. The previous talk covered authentication in a lot of depth. So what you start to do here is you start adding authentication, making sure that the user is logged in, otherwise you give a 401 unauthorized. But a lot of people forget that you also need to add explicit authorization checks. Checking that the user is logged in is not enough. You need to check that he's actually the owner of this task or actually has permissions to access this task information. And that's something that a lot of APIs actually forget. And that problem is known as insecure direct object references, because essentially you have a direct object reference, an identifier, an ID, and the fact that you don't perform authorization checks allows anyone who knows the ID to access that information. And if you have numerical IDs, like most APIs, 1, 2, 3, 4, 5, then this kind of attack becomes really easy, and it happens to large companies like T-Mobile. Citibank had the same thing with account numbers. They forgot to check who was the owner of the account, and you could access all kinds of account information. This is getting information. It can be worse as well. You can delete the task in a very similar fashion. So again, you should kind of check that the user has permission to delete the task before simply granting that request. So a quick recap, so you have some information to look at later. So many APIs forget this check, and the only proper thing is adding authorization checks. There's people gonna tell you different ways of doing this, like, yeah, use random identifiers or stuff like that. But that simply hides the problem. It doesn't fix the problem. So first of all, add authorization checks. Really, really important. And second, a complementary strategy you can use is you can use non-predictable identifiers. That makes it a lot harder to enumerate all of the objects in your database or your backend. One example, UUIDs, that would make it hard for a user to actually, or an attacker to predict what the next identifier is going to be. So it's going to be very hard to enumerate these things, especially in combination with rate limiting. Brings me here. Don't use, well, use direct object reference. That by itself is not a problem, but make sure that you have proper authorization checks. Test whether your API actually enforces them, and make sure that these things are protected. If you want to add authorization checks, you actually need some kind of information to make your decisions. And that brings us to authentication and session management, especially session management. Back in the day, traditional applications, they did sessions management on the server side. You had a server, you had session objects stored away somewhere, and whenever a request came in, the server would look up the right session with the identifier, check whether you were allowed to access this, and perform that. Of course, one of the problems with server-side session management is when you start replicating your API, building a scalable system, then session management becomes a nightmare. You have to use sticky sessions to make sure that the same session stays on the same server. If that server goes down, the session state is gone. You can also replicate session data, but then again, you have to essentially set up a mechanism to do that across all servers, which is again a nightmare if you have a global deployment. So a lot of people are moving towards client-side session management. Build stateless APIs and push everything to the client. Awesome. Use things like a job token and store it on the client. Sounds good, but in practice, it's actually a bit more complicated than simply taking it from one side and moving it to the left side of the image here. There's a lot of stuff that changes implicitly that you need to take into account. One of the things is server-side sessions, they only share an identifier, and the identifier by itself is not sensitive data. Sure, the attacker can try to manipulate it, but if it's long and random, he cannot predict the next session identifier, and he cannot really tamper with the data stored in the session object on the server. So that data is trusted by default. If you put it on the client, this data is no longer trusted. Essentially, this is data coming in from the client, it's untrusted by default. So if you want to make an authorization decision with that data, you need to make sure that you protect that data. You need to make sure that you first of all verify whether it's valid session data, that it's not been tampered with before you make authorization decisions based on that data. And when I tell you, when I show you it like this and I tell you about it, this is like, yeah, of course you need to do that. But I often look at applications for customers, and a lot of people actually forget that they need to do that explicitly. By the way, if you store sensitive information in your session objects, if you, for example, are building a healthcare application, you want to store some medical information there, you'll also need to protect that against unauthorized access on the client. So you need to encrypt that information as well. Very, very important, and something that is often done wrongly. So don't mishandle client-side session data, only use any data provided by the client after having verified its integrity. How do you do that, you might ask? Well, one straightforward mechanism is a JSON Web Token. Who here does not know what a JSON Web Token is? All right, very good. A few words about what you need to know about JSON Web Tokens. These things are base64 encoded. That does not mean that they're encrypted. It's just a transformation of the data. Data is readable with very simple transformation functions, so it does not protect the data stored in here. The interesting part is the purple one, the middle, that's the payload. That contains the data, and the rest is essentially a mechanism to generate a signature and attach it to the token. And the signature, by default, essentially helps you verify the integrity of the token. So the specs support signing by default. Well, support signing, it's enabled by default in almost every implementation, which is a good thing. They also support encryption. Well, the specs do. Implementations, it depends on the kind of library you're using. But there is support for encryption, and you don't need to implement those things yourself. One very interesting part. So what happens is when you generate a JOT token, is you generate a signature, you attach it to the token, and you send it to the client. And when the token comes back, what you can do is you can recalculate that signature and compare it to the original one. Because you're the server, you're the only one that can generate and verify valid signatures. That's very important. It's based on a secret stored on the server, and if you are the only one knowing that secret, then you can verify that signature. If the attacker modifies the data, the signature will no longer match, and you will see that something is wrong, and you can refuse access altogether. One side note here, this is the default mode of operation. Unfortunately, many libraries offer a decode function and a verify function. And what happens there is this is the decode example. So you get a JOT token and you decode it, and out of that you get the data sent from the client. Sounds good, right? Well, this is the verify function. Looks a lot more complex, so who would want to use that? Well, the main difference is the top one does not verify integrity of the data. It simply decodes it from base64 to human-readable, object-oriented format, whatever, and that's it. So if the token is invalid, the top one will not detect that. If it has been tampered with, the decode method will not complain. It will simply give you the data, in this case provided by the attacker. And a lot of, one of the problems is that the decode function, documentation is going to explain to you what it does, but because it's named decode, there's no trigger for you to think about, hey, what am I doing security-wise? Is this secure or not? It would have been called insecure decode or bypass security decode, then you would have been triggered to look at what's going on there. So unfortunately, some people are using the decode function in their backend without thinking about the consequences and building applications that accept any JOT tokens without any verification. So seriously, if you're using this, go to your code base, make sure that you don't use these insecure decode functions and that you actually use the functions that verify the signature before giving you the data. Very, very important stuff. So signatures, I mentioned a server-side secret. Let me show you how signatures on JOT tokens usually work. So you sign with a shared secret, shared as in you only should know it, nobody else should. Why is it shared? Because when you encode a token, you're going to sign it, and you're going to use the secret to generate the signature. And it's shared because it's the shared state comes from the fact that you use the same token to verify the integrity of the same secret to verify the integrity of a token coming in. So this is essentially what we call an HMAC function. So essentially you have a server-side secret, you give it to the function, together with the JOT token, it's going to generate a signature, and you need to know the secret to be able to generate a valid one, and that's why this actually works. However, this only works within your own application. If you need to verify the integrity of your token somewhere else, this is a problem because you only have one secret, and if you hand it out, then the other party can start generating valid JOT tokens. So if you need to verify the integrity of tokens in client-side software, don't use this mechanism. Absolutely never ever do that, because you would have to share your secret with the client, meaning that everybody who can read that secret can generate valid JOT tokens. Same if you use OpenID Connect with Google. Google is going to give you a JOT token. It's going to be signed by Google, but they're not going to give you the secret that they used to sign the JOT token. That would be a security nightmare. So if you want to go that route, you need to use public-private key pair signatures. And this is also a feature of JOT tokens, but it's a lot less known that this is supported. And many people struggle with these kind of scenarios in this setting, and they actually start sharing their secret with other people, third parties, and creating huge security vulnerabilities. So what you should be doing is you should sign, or if you want to share your JOT tokens, they should be signed with a private key. So Google in OpenID Connect is going to sign a JOT token with a private key only known by Google. And whenever you get a JOT token like that and you want to verify it, you use a corresponding public key. So essentially you get Google's public key, it's a public key, everybody can know it, it doesn't matter, and you can use that to verify the integrity of a token. And that's the way you set it up. If you need to do this with third parties, you need to use that mechanism. So again, this is a quick recap for later reference. Many people don't know about these two mechanisms, and because of that, they actually use the wrong one in certain scenarios. A private key should only be known by the service issuing the tokens. So this also works quite well in your own infrastructure. If you want to make a separate authentication service, you can use the private key there, and everything else in your application can use the public key. That also works quite well. So don't use the wrong signature scheme on JOT tokens. That's essentially another security pitfall here. All right, we're working our way deeper into the application. Back to our overview scheme, we have like the server, the backend API server, and we have our front-end application. What typically happens is you do your authorization checks there. So a call comes in, you check who is this user, is he authenticated, what's happening here. And then after that, you call some internal services, some other parts of your application. If you don't have a microservice architecture, this can also be a monolith where you call other features, other parts of the application. One of the things that often happens is that the authorization check remains on the front-facing part of the API, and the internal systems have no idea who is doing what. There's no way to know, am I doing this for which user, am I performing a certain action, and there's also no way to create an audit trail. And one of the things you should be doing is you should be spreading that information throughout your service. Every part of your application in the backend should know for which user he's doing a certain action. And if you know that, you can create valid or valuable audit trails. You can log what is happening in your system. So if there's an incident, if somebody gained unauthorized access to an account, then you can easily see throughout your entire log system what actions have been done in the name of that user. And if you don't have that information, if that information is not present, then there's no way to determine what actually happened and what went wrong. One way of doing that is, for example, with OpenID Connect, you get this JOT token. This is the payload of a JOT token that might be issued. You see a lot of attributes, but you see one of the reserved one is subject here. The subject is going to tell you the identifier of the user or some identifier of the user. There's going to be some custom claims. You can include role-based information there as well, so you can make authorization decisions based on that information embedded in the token. And a final really interesting part is this ACR property. This ACR property here essentially indicates the strength of authentication used by the user. So if you have a system, we have some sensitive parts or some normal parts and some really sensitive parts, you can actually shield those sensitive parts by enforcing that the user needs to authenticate with two-factor authentication before getting access to that part of the system. You can use that property that's right there to check that level of authentication. So not propagating identity information is again a common mistake where the backend systems don't have a good way of determining whether something is really authorized or not, or whether there is an attack going on where the API may be misled into performing certain operations. So now we have a way to do authorization, but we still need a way to get our authorization information or our session information to the server. We mentioned JOT tokens. JOT tokens are a way of representing data. It's not a transport mechanism. So one of the common options here is using a cookie. You can transmit that information with cookies, or you can do so with your authorization header using the bearer value. This is a topic where there's a lot of confusion. So some people say that you should be using cookies or should not be using cookies in single-page application context, should not be using cookies to access APIs, and should be using the other one. Well, both of them have advantages and disadvantages, and I'm going to give you the background information on what actually each of these means and what you need to take into account. For me, both are actually quite valid to use, so it's up to you to decide which one works for you. If you have worked with cookies before, which all of you have, you know that they're a mess. Cookies have like weird security properties. They need to be handled very carefully, and they result in kind of problems as well. But cookies are very compatible with the web. Cookies are the default mechanism of storing state in web applications. And every mechanism that is available in web applications actually works quite well with cookies. So for example, browsers handle cookies automatically, which is great. They store them and they attach them to outgoing requests. Cookies are also present on every request sent by the browser. So if you want to enforce access control or authorization checks on DOM resources like script files and stuff like that, for example, I've had a customer that had an admin interface, and they only wanted to give access to those JavaScript files if you were actually an admin user to prevent leaking information about how that system worked. If you're not using, well, if you are using cookies, then you can easily access or perform those checks because cookies will be present on the call to load that script file. If you're using the authorization header, for example, cookies will not be that information will not be present, and there's no way to add it. And that's going to make it complicated to deal with. That's one of the big differences, and the same holds for core server-sent events and WebSockets. All of these technologies work with cookies, and they do not work with the authorization header. Of course, if you want to use cookies, you need to secure them, and that's really, really messy. You have security flags like HTTP only and secure. You now have a same site flag, which which helps defend against cross-site request forgery, which I'm gonna talk about next. And you even have cookie security prefixes. So now you have a prefix you can add to the name of the cookie. There goes lunch. So you have a prefix you can add to the name of the cookie to make the browser handle it more strict as well. It's a mess. And if you need to support cookies in a non-web application, like a mobile application, dealing with all of this crap is just batshit insane. Which is why a lot of people move to custom headers to use the authorization header with the bearer property. So if you want to use that, they're not handled automatically. So your application will actually need to do that itself. You need to implement the code yourself. And as you can imagine, implementing security relevant features is going to lead to certain problems. I'm going to give an example next. If you have these DOM elements, script tags, style sheets that you need to shield from certain users, there's no way to do that. Or not an easy way. You have to come up with your own system. Actually, a lot of people that have been using the authorization header are starting to use a hybrid system with cookies as well to make sure that they can do certain things. Same with WebSockets. If you need to set up a WebSocket connection, you call the constructor new WebSocket, there's not going to be an authorization header there. So if you need to do authorization there, you again need to come up with a custom mechanism to deal with this. And this makes the authorization header less useful in certain scenarios. I'm not saying it's a bad option, I'm saying you need to think about which fits better for you. Actually, securing these things is also surprisingly difficult. Where do you store the data in the application? Local storage, that's the most common option, but that has certain consequences. There's no way to shield it from malicious code in the same origin, for example. And also, if you send it to outgoing requests, you attach it to outgoing requests, it's likely you're gonna mess up that as well. So, by the way, these headers are very compatible with other types of applications, which is why they're so popular. Here's one example of how to mess up sending the authorization header on outgoing requests. This is an example from an AngularJS application, from a tutorial I found online by Googling for 2 minutes. Essentially, what's happening here is you intercept a request. This is Angular 1, but the same holds for Angular 2. Well, 5 actually. This is a request, you intercept it, and you add a header to the outgoing request using the token found in local storage. Sounds good, right? Actually, a lot of people implement it like this, and this works perfectly fine as long as you make calls to your own backend. You set it up, you make the call, everything works, you're happy. And 2 months later, your boss asks you, hey, can we integrate this third-party API? And you're like, yeah, sure, it's Angular, I can do whatever I want. So you implement this. And the moment the call goes out to the third-party API, this interceptor will be like, oh, this is a request. I'm going to add this authorization header with the bearer option and my token from local storage. And now you're sending your tokens to third-party APIs, just like that. And you won't even see this. If you don't look for that, this just happens in the background. And the third-party API now has your user's tokens. And he can use that for whatever he wants. So again, one of the pitfalls here is switching to a new mechanism and kind of minimizing the impact of that new mechanism. Cookies are messy for sure, but they have been around for very long and we actually understand quite well how they work. And these new mechanisms often result in new problems that we need to take into account. And this again seems simple when I talk about this here in front of you, but I can promise you I've seen this in applications. I did a workshop at an Angular conference last week, and half of the audience was like, oh crap, I need to look at my application. And these are experienced people, so this actually happens in practice. All right, next topic is cross-site request forgery. Cross-site request forgery, or CSRF in short, is actually a cookie-related problem. Let me show you what it is, and then you can decide whether your application actually suffers from that or not. The setup here is we have a browser, the user's browser, and we have 2 servers. We have a legitimate application server, where I'm going to log in, I get a page, I get a cookie. Doesn't matter what kind of system this is, front-end application, back-end, whatever, or traditional application. The one thing that matters is that we have a cookie that's going to be attached automatically. In a CSRF attack, a third-party context, in this case, just any other website with probably with cat pictures, whatever you want. Maybe in Poland it's like vodka bottles or something, I don't know. Anyway, what you're going to do here is that page is going to send a request to the backend of the legitimate application, and the browser is going to attach a cookie there as an outgoing request. That's automatic behavior by the browser. If the backend is not aware that this call is coming from a totally different context, he's going to execute it as a legitimate request. And that's cross-site request forgery, or the essence of cross-site request forgery. So essentially it's cross-site because one context from a different website is making a call to the backend of a legitimate site and triggering a state-changing operation over there. CServe is actually, can be quite dangerous. One example where CServe is rampant and has been abused quite a lot are home routers. Access points in your home. Everybody has one of these, probably. And they have a web interface. And they think we're on a local network. We're in a very secure environment. We don't need to care about security. And they actually don't care about security. So what somebody figured out is that you can actually change DNS settings on these routers using CServe. You can simply make requests in the backend to your router. It's not very hard to predict where it's going to be. It's 192.168.0.1 or 10.0.0.1 or whatever. They can start guessing and trying to change your DNS settings. And once they change your DNS settings, they can send you wherever they want. So if you want to go to your banking website, they can easily redirect you to a fake website and serve you whatever they want from there. This actually happened in South America some time ago, and they actually hit about 300,000 of these routers to change DNS settings. So that's a massive attack with some serious consequences. That's what CServe can do. Now back to your API. So CServe exists because the browser is very liberal with cookies. He attaches them to outgoing requests. So in the API, this means that you need to make sure that if such a request comes in, that you actually are able to detect it. And typically you need to worry about post requests, but a lot of APIs also support or allow the execution of post-like operations with GET requests. So many APIs support either a post with parameters in the body or a GET request with parameters in the URL, and they handle that the same way. So if you do that, then only looking at post requests is not going to cut it. There's one, well, the tradition, sorry. Let me first talk about CServe for 2 seconds, and then we're going to talk about cross-origin resource sharing and how it's related to CServe in this case. So the traditional defense against CServe, which has been around for 15 years, is hidden form tokens. So a normal GSP application, ASP.NET, whatever, would use hidden form tokens. You can imagine in an API, hidden form tokens is probably not going to work too well. So in the API world, we have a different defense. And what we're going to use are hidden tokens, or transparent tokens. Essentially, the setup of this defense is we're going to send a second cookie along with the first cookie containing our session information. And whenever a call comes in, the application, the front-end application or Angular application or whatever, is going to copy the value of this cookie to a custom header. So it's going to copy the value of this XSRF token cookie to a custom header called XSRF token. Yeah, sorry for the bottom part of the slides. My apologies for that. Essentially, that's enough. The application here, at this endpoint, the application is going to check whether the value in the cookie matches the value in the header. And this defense actually works because if you have a malicious application trying to make that call, the browser will attach those cookies. But this context will never be able to read cookies from this context. That's not allowed browser behavior. The browser will prevent you from doing that. So that application will not be able to attach this custom header with the right value, so the server actually knows that this is not a legitimate call. That's how we can do CServe in API systems. That's, by the way, this mechanism is supported by AngularJS by default. So an Angular application automatically looks for this XSRF token cookie and automatically attaches it to outgoing requests. Some people think that CServe, well, CServe is an API is a bit of a complicated setup. And you have, it becomes more complicated if you start looking at the whole picture, which includes cross-origin resource sharing, or CORS. So let me try to explain this as clearly as possible. Cross-origin requests, like the one that lead to CServe, have always existed. You've always been able to submit a form to a different backend. And that's the original cause of CServe. So whenever cross-origin resource sharing has been introduced, now you can make the same calls with XHR. You can do them from JavaScript. But there's two kinds of calls that you can do from JavaScript. You can do the traditional ones that look like a form call that you have been doing in the past, or you can do a new and fancy call like a cross-origin put request or a cross-origin delete request, which have never been able to be sent from a form. And that's where CORS becomes complicated, because CORS is going to make a distinction between those two types. If you have the traditional HTTP requests, aka those you can generate from a form, then you need to implement CServe protection. Because those can be, you are making them from XHR, but an attacker can make them with a form and make sure that they reach your backend without problems. If you are using non-traditional HTTP requests, so essentially everything you cannot generate with a form, if you're using custom content types like application/JSON, then you can rely on the protection offered by Crossorigin resource sharing. And the protection is essentially going to make sure that your backend needs to approve that call before it's going to be made. And if your backend does not explicitly approve that call, then the browser will prevent that from happening and will protect you that way. I'm going to talk a bit more about CORS in the next slide, so that should become clear. So, to recap, I know this is a bit of a complex topic. So, CSRF is actually quite an important attack. It matters when you're using cookies. If you're using the authorization header, CSRF is not an issue because you need to attach the token manually, and an attacker will not be able to do that from outside of your application. So the only way for an attacker to do that with the authorization header is to run script inside your application, and if you can do that, then you're screwed anyway, so CSRF does not matter. If you're using cookies, then an attacker can make a call with session information available. Then you need to make sure that if you accept traditional requests, form encoded data, stuff like that, that you implement proper CSRF protection. If you don't accept such requests, you can rely on cross-origin resource sharing and implement a strict CORS policy. All right. This is the last complex topic, and then we're going to go back up and wrap it up. Cross-origin resource sharing, again, my apologies for the image on the bottom of the slide. Essentially what happens in CORS is if you have an application running somewhere and it's going to make a cross-origin XHR call, like this, that the browser is going to make sure that your application actually expects that call. So in this case, it's a GET request, but you can also use post, put, delete, whatever method you want there. This is fairly new browser behavior. It started with Firefox 4 or something, and it's something that probably every one of you relies on every day. What's going to happen is when you make that call, the browser is going to see, hey, this is a cross-origin XHR call. I'm going to add this origin header. I'm going to inform the server to tell him where I'm coming from. And essentially, this origin header contains, in this case, app.beersafe.eu, and it's going to tell the server, hey, this call comes from a different context. Are you sure you want to accept that? And if the server wants to accept that, he needs to add custom response headers. He needs to add the access control allow origin header. And that's going to tell the browser, hey man, I am fully aware that this call is coming from a context with that origin, and I'm actually allowing it to access the response. This is for the simple case of CORS requests. The more complex ones, the ones that you can never generate from an HTML, from a form, there's going to be a first step where the browser asks the server, hey, are you okay with me sending a delete request to this endpoint? And the server has to respond positively before the browser actually makes the call. Would take me too far to go into details. If you have questions about that, come talk to me after the presentation. What I wanted to talk about here is, a lot of you are probably deploying CORS policies. And CORS policies are often misconfigured, and that's potentially very dangerous. Take the example here, if you look at the example here, the endpoint is to request an API key. If this endpoint is configured insecurely and hands out API keys to every origin asking for it, you're in a lot of trouble. And this is actually based on a blog post from a security researcher. Again, the references are in the back. And he found exactly this problem on a Bitcoin endpoint, and Bitcoin exchange endpoint. And you could request an API key, and with that API key, you could access a user's Bitcoin wallet, which, as you can imagine, with the value of Bitcoin today, is quite a problem. So these things, again, happen in practice. And I wanted to give you a few options of how people screw up CORS policies to make sure that you can check your own policies for those mistakes. And you can see what is going on there. First, this is the origin header as you get it from the browser. A first problem is if you only check for partial matches of that origin header. So if you check whether, check against, for example, this value, somebody can easily create a website called beersafe.eu.evilattacker.com. And if you check if the origin that you get starts with this value, you're in trouble because it's going to match, and you're going to think, oh yeah, that origin is trusted, and you're going to send back the wrong header. If you allow null as an origin, so for some reason people allow null as a valid origin, an attacker can easily fake the null origin by sending a request from a sandbox container, a sandbox iframe. So that's really easy to trigger, so if you allow that, you're in trouble again. If you only check the domain and not the origin, if you would check for beersafe.eu instead of HTTPS, beersafe.eu, that allows an attacker to launch requests from HTTP, which can easily be faked. And the last one is the best one. Some services simply reflect back the value of the origin header. So they reflect back whatever they get, and everything is allowed. And if you do that, your API is wide open for any client-side context to access, which is potentially a big, big problem. Here's an example of such a configuration. Again, if I Google for these things, I easily find them. So I'm not sure what kind of software this is, but this is an Apache config that I recommend. And here they, they read the value of the origin header, and here they simply add that value back in the access control allow origin header. So essentially they accept calls from everywhere, which is not what you want to do. And to make it even better, here they acknowledge that the browser can use cookies to make that call. So essentially, if you have an SSO endpoint that uses cookies to check whether you're logged in and gives out API keys, configure it like this, everybody can grab one and everybody can access your API just like that. So don't do that. Don't screw up your course implementation, please. All right, still with me? I have two more to wrap up, but they're going to be a bit easier, so you can relax now. Should your API accept something like this? Is that valid input? It depends, right? Maybe, maybe not. Brings me to the topic of input validation. Input validation is something that some people would consider the most important thing. I'm not sure whether it is, but I just wanted to talk about this for a short while. This looks like SQL injection, so maybe it's valid, maybe it's not. And input validation is one of the most important first lines of defense. It's going to help you weed out strange things that you should not be dealing with in the first place. So every data coming in is untrusted. So you should make sure that you actually enforce some restrictions. And a couple of best practices here are, you should only accept content types you expect and reject anything else. So if you have a JSON API, don't accept any other content type from the browser except application/JSON. Just like that. Some APIs accept text/plain and try to parse it as JSON, but if you start doing that, you're going to run into problems. So don't do that. Just refuse anything else and actually manually check your API, or automatically, whatever, check your API that it actually enforces that restriction and barks at everything that's not JSON data. Validate input types against their data types. So in the example I gave here, if this is an identifier, a numerical identifier, this should not be valid input. This should be rejected from the first step in the system. It should be like, no, this is not a number. I expect a number, so go screw yourself, essentially. Go away. Impose sensible length restrictions. Again, for certain content types, this is easy. Other content types, there should be an upper limit. Don't accept 5 megabytes of text input and try to work your way through it. It probably doesn't make sense unless you actually expect 5 megabytes of text input. But set a reasonable limit, like 1,000 characters is probably not going to cause problems for usernames or passwords. So that's a nice upper limit to make sure that nobody is able to DDoS you with such a simple technique. And use secure parsers to process input. There's a lot of vulnerabilities popping up in parsers that are easy to abuse if you know how. So make sure you have a decent library and keep that library up to date. So the lack of input validation is, in my opinion, it's very important, but it's not the most important security mechanism in the API. And the reason that it's not the most important thing is because it's not going to protect you against any attacks if you don't get it right. So it targets the symptom. It targets somebody trying to inject something. But if you still don't use prepared statements to build your SQL queries, you're going to run into problems one day, sooner or later. So the only real fix is writing secure code. And input validation should not be relied on as the only defense. It's a very good first line of defense. It's very good to read out the very strange things right from the beginning, but it should not be the only thing that you're doing. Because once your data is complex enough, if you're accepting rich text format, HTML documents, good luck trying to validate that when it reaches the input, the entry point of your API. There's no way you can actually start doing that. And if you don't believe me, take a look at XSS filter evasion cheat sheets. These are pages and pages and pages of ways to evade certain filters on the server side with some strange XSS payload. So this thing is really, really problematic. And sometimes in an API world, it's not even your problem anymore. Take cross-site scripting for an example. If you have an API, the API will never be able to protect the client against cross-site scripting. That's a client-side responsibility the moment you're serving data instead of web applications. So think about those things and don't rely on input validation as a security mechanism. Use it as a second line or as a first way to weed out strange things entering your API. And that is actually the last one I wanted to cover. So To wrap up, I could give you an overview of every every best practice again, but that's probably going to be way too boring for you, so I'm not going to do that. I'm going to send you away with the best advice I can give you, and that's question everything. We have been building web applications for a long time. In an API world, things change. So question everything. Think about what's different when we push client-side session data to the client. What do we need to take into account? Do we really understand what we're doing? And things like that. So seriously, this is the best advice I can give you. So now it's up to you. Like I said, I'm a trainer, so I usually end with the advice, go build secure applications. That's what you're supposed to be doing. Follow me on Twitter if you want to stay up to date, if you want to grab a copy of the slides, they should be on there. And the final thing is share your experiences. If you do something security-wise, share this within your company, share this with your colleagues, go to a local meetup, do an OWASP chapter, talk there, and maybe, who knows, you're here next year to give a talk about how you address security in your system. Thanks for listening. If you have questions, I'll be around here after the talk, so please come up and we can have a discussion about whatever you want, security-wise. Thank you.